Hi, this lesson is about getting information from the graph of a function. So when you have the graph of a function, you always read it from left to right, the same way you read text. So for the following example, we have the graph of h of x, and we want to answer the following questions about h of x. So part A says to evaluate h of -3, h of 0, and h of 3. That means you want to know what the y value is when the x value is -3, and then when the x value is 0, and then when the x value is 3. So the number inside of the parentheses are the x values, the number that you read along the x-axis or the horizontal axis. So when x is -3, your y value is way up here, it's equal to 4. So h of -3 is 4. When x is 0, your y value is also 0. So h of 0 is 0. And h of 3, that's right here, the y value is equal to 5. So h of 3 is equal to 5. For part B, you're asked to state the domain and the range of h of x using interval notation. So in terms of domain, you want to read the x value. So it looks like this graph is defined from -3 all the way up to 4, including -3 and 4. So we use brackets. The domain is from -3 to 4. And with your range, you want to read the y-axis from bottom to top because you always want your intervals from smallest to largest. So the first y value that appears is this one. That's the lowest point on the graph. And then they get bigger from here, and they get bigger from here. And the biggest value is this one right here. So your range is from 0, which is this point, your y is 0, and 5, which is the highest point on the graph. So it's a closed interval from 0 to 5. In part C, you're asked to find the values of x where h of x equals 2. So for part C, you're given the value of y, and you want to figure out what the corresponding x value is. Well, y is 2 in two places, right here. That's the value that corresponds to 2, and right there. So for the first point, it looks like that x value is -2. And for the second point, it looks like it's right in the middle of 1 and 2, so 1.5. So h of x equals 2 at x equal to -2 and at x equal to 1/2. Okay, for part D, you're asked to find the values of x where h of x is less than or equal to 4. Here again, you're reading the values of y. Where are the y values less than or equal to 4? And you need to state the answers in terms of x. Well, 4 is here. Okay, so anything below those points here, here, and this one's also a value of 4. Anything below that would be less than or equal to 4. So equal to would be exactly at those points, and less than would be below that. So that would be all of these values of x, and then the values from here to there. So that's this part right here. So h of x is less than or equal to 4 from -3 to 2. And then, and this is a mistake, and then also from, oh no, sorry, this is 5. So this was incorrect, what I stated earlier. So up here, these values are not less than or equal to 4, they're greater than. So it's equal to 4 right there. So it is less than or equal to 4 from -3 to 2, and then again at the value of 4. So which is why just the 4 is in the curly brackets, just to indicate one single point. Okay, then for part E, you're asked to find the net change. So that's something that was discussed in an earlier lesson. And the net change is the difference in two y values. So we need to figure out what the y values are of this graph when your x's are -3 and +3, and subtract them. And you always want to subtract with the bigger number first. So your net change would be h of 3 minus h of -3. So h of 3 has a value of 5, and h of -3 has a value of 4. So 5 minus 4 gives me a net change of 1. Okay, so that answers the first question. So let's go on to the next example. Um, so before I cover that example, let's just make sure we understand how to read a graph again when you're talking about increasing or decreasing. You read a graph from left to right, and a graph is increasing if it's going upward from left to right. And if that's true, then when x sub 2 is greater than x sub 1, then f of x sub 2 will be greater than f of x sub 1. So in other words, the number to the right of another number, x sub 2, is bigger than x sub 1, then the y value is also bigger than the one before it because it's going upward. And then the opposite is true. A graph is decreasing if it's going downward from left to right. So if x sub 2 is greater than x sub 1, then the opposite um, scenario happens. The function value, the y value, is less than the one before it. So f of x sub 2 will be less than f of x sub 1. You can express intervals of increasing or decreasing as open intervals in terms of x. So when you're asked to determine on what intervals a graph is increasing or decreasing, you want to express that in terms of x. Even though you're looking at the behavior of the y values, you want to express your answers in terms of open intervals in terms of x. Okay, we have several types of points on a graph, and those are called extreme values. And so we start with a local or a relative maximum. So these two words are synonyms, they mean the same thing. So a local or a relative maximum is the highest or greatest point on a graph within a small interval of the independent variable. A global or absolute maximum, these are also synonyms of each other, is the highest or greatest point on a graph within the entire domain of the function or everything that you're possibly considering on a graph. So this will be the highest point overall. This could be a high point within a small interval. So you could have more than one of each of these. And a local maximum could also be a global maximum. So I'll be showing you graphs to um, give you examples of these. Then we have local or relative minimum. Again, these are synonyms of each other. So a minimum point will be the lowest or smallest point on a small interval within your graph, and then a global or absolute minimum is going to be the lowest or the smallest point overall on the domain of a function. When you're talking about the plural of a maximum or a minimum, those will be called maxima, meaning more than one, and minima, meaning more than one minimum point. When you're discussing them in general, maximum or minimum, those are called extrema or extreme values. So a maximum or a minimum would be considered an extreme value. So an extrema is the plural for more than one maximum and or minimum. You can have an absolute extrema, and it can also be a local extrema, as long as the values of x where the extreme values exist are inside of the domain and not on an endpoint of a domain or an interval that it's graphed on. So you can have local extrema within the domain of a function, but not at the end point of a domain. So some functions have a beginning and end. They're not all real numbers. So you won't have a local or relative extreme value on an endpoint. All right, so here's a picture. We want to identify the global and local extrema. Remember, extrema means maximums or minimums on the following graph and the intervals, and define the intervals where the function is increasing or decreasing. All right, so here's my graph drawn in this dark blue color. My extreme values are the points in like this hot pink. So this is considered to be an absolute and a local minimum at 1, -1. That is the lowest point overall on the graph. There is nothing lower than that on the graph. So that's what makes it a global extrema. But it's also a local extrema because it's within the domain. The domain here looks like it's all real numbers. There's no beginning and end to this. These arrows that you see here. Um, so it's within the domain, but it's also the lowest one overall. So it's both a global and a local extreme value. It's a minimum. Then this one here at 3, 1 is considered to be a local maximum. That is the highest point on a small interval before and after 3. So if I look at values close to 3 before and after 3, that is the highest point overall, but it's not the highest point on the entire graph. There's infinitely many points on this side that are bigger than that value. There's infinitely many points on that side that are bigger. So it is not a global extrema, only a local. And then this one here at 4, it looks like 4 3/4 approximately. That's a local minimum, not a global, because remember this one was the global. So this is a low point within a small interval close to 4, but it is not the smallest point overall. So those are all my extreme values, the pink points that you see on the graph. When you're reading increasing and decreasing, you read it from left to right. So despite this arrow pointing upward, when I'm reading from left to right, it's going down first, then it's going back up, then it's going down again, and then it's going back up again. So we're going to express that in terms of interval notation. It's increasing from 1 to 3, and then again from 4 to infinity. And it's decreasing from negative infinity all the way from here to 1. And then this little piece right here, it's also decreasing from 3 to 4. And those intervals of increasing and decreasing should be expressed as open intervals. Okay, so let's move on. We can determine where two graphs intersect by setting them equal to each other. So if you need to find where two graphs intersect, you're basically setting them equal to each other and solving for the variable. So here, if I want to figure out where f of x equal to x squared and g of x equal to 2x plus 3 intersect, you're just setting f of x equal to g of x. Now, once I do that, you can see that I have a quadratic equation and I want to set it equal to 0. Once it's set equal to 0, you have options. If it's factorable, that's probably the quickest way to solve it. But you can also solve this with the quadratic formula and get the same answer. So x squared minus 2x minus 3 factors into x minus 3 and x plus 1. That gives you two solutions, 3 and -1. 3 and -1 are the x coordinates of the point of intersection. The way you figure out the y values is that you plug in 3 into either one of these, and that'll give you the y value. So it doesn't matter which one you pick. If I pick f, 3 squared, that gives you 9. If I pick g, that's 2 times 3 plus 3, that also gives me 9. So they should be the same y value. So that's why the first point of intersection is 3, 9. And when you plug in -1, again into either one, you get a y value of 1. So 3, 9 and -1, 1 are your points of intersection for these two graphs. And that will be a really useful skill as you move on in mathematics. So make sure you know how to figure out where two graphs intersect. So here's a picture, the graph of two functions, f and g. F is in blue, g is in red. And you can definitely see that these two graphs intersect somewhere. And I highlighted the points of intersection in green. That's where f and g would be equal. So we're going to answer some questions regarding this graph. Part A says, which is larger, f of 3 or g of 3. So f of 3 is the one in blue up here. G of 3 is the one below. Since the one in blue is higher than the one in red, the y value is bigger. So f of 3 is definitely greater than g of 3 on this graph. You weren't asked for what the value is. You just were asked which one is larger. And so this is the greater than symbol. Next question is, for what values of x is f of x and g of x equal? Well, that's where these green points are. Those are your points of intersection. So they're only asking you, what are the x values where they're equal? Well, they're equal here at 2, they're equal here at 5, and they're equal here at 7. So f of x and g of x are equal at 2, 5, and 7. And part C, the question is, for what values of x is f of x greater than g of x? So that means, where is f of x higher than g of x? Where's the blue graph higher than the red graph? So that definitely occurs from here to there, and it definitely occurs here. Okay, so f of x is greater than g of x from 2 to 5. And then again, this is open because at 2 and at 5, they would be equal. So that's why it's open. But it's also greater from 7 to 8. And notice that 7 is open. I use the parentheses because at 7, they're equal. But 8 is a closed interval because at 8, f of x is definitely greater than g of x. They're not equal. So that's why I want to include 8 in this interval here. So that one is closed. Okay, so here's an example that you can try. It says, given the graphs of f of x and g of x, just make this a little smaller so you can see. Here are your two graphs. F of x is the one in red. That's a third degree polynomial. G of x is in blue. That's a line equal to 3x. And the question is, for what values of x is f of x equal to g of x? So that would be, again, looking for where the two graphs intersect just by reading the graph. Part B says, for what values of x is f of x greater than or equal to g of x? And then the last one is, for what values of x is g of x greater than f of x? So you can give that a try. Good luck.